Hello world, this is Craig. I started a new project where I need a command processor, where in other words the user is going to type a letter on the keyboard, and depending on what letter they type, I'm going to go off and process this command. This is for another confidence test that I have for a piece of hardware. And following on yesterday's video about the stack pointer, I got to thinking, well, maybe I was a little bit down about the stack pointer and you know, not really showing how it can be utilized, you know, for the good of all. So I thought, well, let me combine the two. Since I'm writing a command processor, and I mentioned yesterday that the stack pointer can be used for branch tables, let me go ahead and talk about branch tables and compare immediate command processors. So when I'm writing code, quite often this is what it winds up looking like. Let's say this is a type of program where the user is going to be entering a command, single character commands. I'm going to look at that command and go off and do something. So quite often when I start writing that, I'll just use brute force compare immediates. So this is an example where I have a little loop here. It's called user in. The first thing I do is I call a command input. And then I look at that command. That command's going to be in the accumulator, so I compare immediate with various things. So in the first step here, I compare immediate with a question mark and say, is this a help? So user asking for help. Well, if it is asking for help, if it is equal to the question mark, then I jump with 0 and I go to the branch called CT help. If it's not a question mark, then I compare it to something else. Compare it to a 1, and if that's a 1, then jump to group 1. If it's not, go on down the line. And so you finish going down this line, or you finish going down this program line by line, comparing it to all the options that you've written into for these branches, and you get down to the bottom, and if it hasn't matched anything, then you just jump to a routine called error. Okay, and you can see that each command to process it, or to have it in this table, takes 5 bytes. The CPI, compare immediate, takes 2 bytes, and then the jump takes 3 bytes. So a total of 5 bytes for every command that's in here. And now if we look down at the actual routines, and I don't have the routines in here, these are all just, you know, little placeholders for the routines. But if we look at the routines, if I'm going to jump back to the user in when I'm done with this routine, so here's my CT help sub, and then I'm going to do it, I don't show it here, but there's going to be a bunch of commands in here, and then that's going to end with a jump back to the user in, and that takes 3 bytes. So basically we see that for each command to process, it takes 5 bytes to get there and 3 bytes to get back. So that's a total of 8 bytes to do this. And there's no overhead, and it's very simple, and you can just add on to this and tack on and add more and more things. It's a very simple way to do it, and I find that quite often my programs start out looking like this. Now let's look at the same thing, only using the branch table. So here's our branches, and keep in mind that just as before, there's a lot of code between the label and the end of the branch, but in this case we're going to end the branch with the return. So you can see here's our help branch. It's going to be a bunch of code in here to give the user help, and then at the end of that branch there's going to be this return instruction. So the first thing you notice is that each branch only requires 1 byte in addition to the code in the branch. Just that 1 byte for the return. Where before, when we were doing the compare immediate and we were jumping back, it required 3 bytes, the jump instruction, and then 2 bytes for the address that we were jumping to. If we look at these branches, we can see that these are all of the labels. There's all the missing code here, each of them ending in the return. And in the left-hand side, these are the addresses that the assembler has assigned for that branch. So for example, the CT help branch is at address 0056. Okay, so those are our branches, and they're exactly the same as they were before. Now let's look at the little bit of section above that. This is our branch command table. So this table, we have said, okay, we're going to have a data word, and that data word is the label for CT help, and that is the branch for the help command. If the user types a question mark, that's where we want to branch. The assembler then has converted that and said, okay, the address for CT help was 0056, and so that's what it's going to put in that data word. So if we looked at these data words in ROM, this is what they would look like on the left-hand side, this column of addresses. And these are the addresses of the branches. So the CT help address is 0056, the error branch is address 0060, and so forth. We now have our command table, which contains all of the possible commands. And this has to be continuous, the way that I've written this code, meaning that the question mark is the lowest possible command and the Z is the highest possible command. And by lowest and highest, I mean according to the ASCII table. If we look at the ASCII table, we can see that the question mark is 3F in hex and the Z is 5A in hex. So what we're saying is that table has to be complete between 3F, which is the question mark, and all the way up to Z. So if you look at our branch table, we have all the possible commands. There's a question mark, there's the @ sign, and then there's all the uppercase letters from A through Z. Okay, so that's our complete command table. So we have our branches, we have our command table that contains the addresses, the starting addresses of all those branches. Okay, so now let's go up and look at the actual overhead to do a branch table. So just like in the Compare Immediate, we call a command input, so we get our command, and the first thing that we have to do is to utilize the return on the end of the branches. We have to put the return address onto the stack. So we do an extended load immediate into the HL pair of the user in label, which is our little loop here that we're running. So before, where we had to jump to user in, we're now going to put the user in address on the stack. So LXI H user in loads the user in address into the HL pair, and then we push that onto the stack. So the stack now has our return address. We then look at the input from the user, because that's in the accumulator. So we subtract off the question mark. The user put in a character that was between the question mark and the Z in ASCII. We now subtract off the value of the question mark, so that's going to give us a number between 0, or starting at 0, and going up through the highest command, or the last command in our table. So we have a number that's between 0 and, in this case, 27. If the number is less than 0, so in other words, they entered a ASCII command that had a value that was less than the question mark, then we want to jump to the error, because that's not a valid command. We then compare that to the length of the table. In this case, that's 1C. We can look at our hex converter, and 1C in hex is 28. So that's the length of our table. So we say we compare that with 28, and if the command is larger than that, then we jump to error. So we only accept commands that are from 0 to 27 inclusive. Okay, so that's the length of our table. So the next step is we load into our HL pair the beginning address of our command table. In this case, we LXI H the command table, and you can see the assembly instruction of that. LXI is 21, and it's going to load into the HL pair the address 001E, which is the beginning byte of our command table, which is again the addresses of all our branches. We're going to clear the D, because we're going to need the DE pair. So we're going to clear D, and then we're going to put into E the value that was obtained from the user after we subtracted off the question mark. So we have an E now, our offset. It's our value between 0 and 27. We then add that value, number between 0 and 27, the offset, to the branch table base address. We have to do that twice because each entry into the table is 2 bytes. So we do a double register add of D to HL, then we do another double register add of D to HL. Remember, the DE pair has the offset, HL has the base. So what we now are doing is changing the HL pair so it's pointing to the address of the branch that we want to go to. We then move from that memory location. Remember, M is just the memory location pointed to by the HL pair. We move that into A to get the least significant bit of the address. So in this first case, if we're pointing to this fail-safe test, it's going to put 5A into A. That's the lower byte. And it's then going to increment H. So now we're pointing to the high byte. Then we're going to move the memory into H. We're done with the HL pair, so we're going to take the memory value, put it into H. We're going to take our low byte and put that into L. So before the HL pair was pointing to the command table, now the HL pair is pointing to the address of the branch. Okay, so a little bit of slickery there, but that's what we've done. We've changed the HL pair from using it as a memory location and pointing to the command table to now pointing to the address of the branch we want to go to. At this point, we have our return address on the stack. We have in the HL pair the address of the branch that we want to go to. And so what we do is we load the program counter with the HL pair. So what that's going to do, we have directly changed the program counter, meaning we have directly changed where the program is running, and we have set it to start running at the beginning of that branch. It's going to execute the branch. At the end of that branch, it's going to get down to the return. It will pop off the address that we previously pushed onto the stack, and that address that it's going to pop off is the user in address. So that's going to take us back to our loop. Okay, so that's a simple branch table. So you can see the difference between a compare immediate and the branch table. The question now becomes, what are the costs and benefits of either one? So the benefits of the compare immediate, the way it was written here, where we jump back from the branches. The benefits are that it's very simple. We just kind of, you look at a value, you compare it, and if it's what you want, you do that. If it's not, you skip on to the next one. There's little or no overhead code. So we immediately started with the first compare immediate. There's not this overhead code where we're creating all the rigmarole for the branch table. And the way that we have written this, it doesn't require the stack pointer to be initialized, which is convenient because I use this a lot for confidence tests and diagnostics where I may not have even started the stack. I don't even know if my RAM is good yet. The downsides of the compare immediates are it's fairly inefficient because every time that we have an instruction come in, we have to go through this long list of possible instructions. And the execution time can vary with the command. If we happen to have gotten the first command right the first time, so the user in this case entered a question mark, bang, it returns right away. But it's possible that we have to go through this entire command list before we find the right one. And that's not so bad if there's 5 or 10 commands, but if there's a lot of commands, that can take a long time to go through this whole list. And there's a big difference then between hitting the first command and having to go all the way through the last command. And the final cost is, for some reason, these compare immediates will drive programmers into fits. They just look at this and it just makes them cringe. What are the branch table benefits? Well, they're actually easier to maintain once you put them in. They're very simple. Like for example, let's look at the command table. If we want to change this or add to this, it's very easy to come in, look to see which commands haven't been assigned yet, and put new code in for that command. And it's easy to change things. It's just a little easier to read than the compare immediate. It gets more and more efficient as the command list grows. So once we have done our overhead, you can see we are adding each additional command with only 3 bytes. So we've got 2 bytes for the address in the command table and then 1 byte for the return. So it's not going to get better than that. We can add as many commands as we want and it just gets more efficient. Has the same execution time for each command. So whether the user enters the first command or the last command, it has the same execution time. The downsides are there's this more setup overhead. We have to do the setup. We have to do more error processing on the command to make sure it's a valid command. We then have to do this rigmarole where we change from the command table and then from that command table actually get the address of the branch. So it can be a little confusing at first. And one thing I didn't have on my costs and benefits here is that the command table, the way that we've done it, where all we're doing is receiving a command and testing that to make sure it's not less than the first command and it's not greater than the number of entries in our list, that means that we have to have all of the commands included in our command table. Meaning that if we wanted to include numbers, for example, we would have to have everything all the way down to 0, which is 30. If we wanted to be able to go all through the upper and lower case and have them as different valid commands, we would have to have a very large command table. We'd have to go all the way from 30 all the way up to 7A hex. So you can see that just with our simple comparison of making sure it's within our command table, we have to have all of those bytes even if we're not using them. So in a sense, that makes it more efficient as the command table grows, because for a lot of those, I counted that we had to have 3 bytes for each command, but our command table has to have 2 of those no matter what. So really each command only adds 1 byte to it as long as we're fitting within our command table. So we have to have all of those other bytes as overhead. So let's back up a bit and mention that either one of these can be used with or without the stack. In the Compare Immediate, we could have at the very beginning loaded immediate, the user in into the HL pair just like we did in the branch table, and then pushed that onto the stack. And then with each of the branches we would have used a return instead of a jump. Okay, so we could have created the compare using the stack, and it would have shortened it. It would have made it so that each of the branches only required the 1 instruction, just like the branch table. We also could have written the branch table without the stack. So instead of using the LXI H user in at the beginning and pushing that onto the stack, we could have dropped those 2 instructions and then at the end of each branch used the jump back to the user in. So either of them could have been either way, and the way that I have shown the code is the worst case of the compare and the best case of the branch table. So to be fair, let's look at the actual byte comparison if we use the stack and don't use the stack. If we use the stack, we have 4 setup bytes. That's where we have to do a LXI of the into H of the return address and then push that onto the stack. If we're using the table, our total setup, our overhead was 27 bytes. And then per command for the Compare Immediate, we've got 5 bytes. So with the Compare Immediate and the immediate data is 2 bytes, and then the address that we're going to jump to is 3, so that's a total of 5 bytes per command. When we're using the table, each table entry requires 2 bytes, so each command only requires 2 bytes, but that comes with a big caveat, because if we only wanted to use, for example, the characters A and B, or A, B, C, D, E, as long as we wanted to use sequential characters, we would only need those 2 bytes per possible command. But anytime we want to skip, so in this case, we didn't want to use everything between the question mark and Z, we wanted to skip some of these. And what that means is anybody we want to skip, we have to count in our overhead. So in this case, we had 54 bytes, and of those, we were only using 10 of the commands. The more sparsely populated our command table, the less efficient that becomes. And then per branch, we only need 1 byte for the return instruction. Now if we do it without the stack, things don't get much better for either one of them. The setup drops just by the bytes that it took to push the return address onto the stack. The per command stays the same, and the per branch just changes from 1 to 3. So whether or not we use the stack, neither of these methods has a clear advantage. 2 key takeaways. The Compare Immediate processing time varies with each command, and that can be a big problem. The branch table, its big downside is the utilization of the command table. If it's 100% utilized, then it becomes very, very efficient. Okay, well that's it for this video. Thank you. Bye.